The act of respiration is the most fundamental and frequent biological process of human existence, occurring approximately 20,000 times every day without conscious effort. During each inhalation, the lungs are filled with a mixture of gases that is commonly and simplistically referred to as air, a term that carries connotations of life-sustaining oxygen and environmental purity. However, a precise chemical analysis of this atmospheric fluid reveals a striking and counterintuitive reality. The overwhelming majority of every breath taken is composed of an element that is fundamentally indifferent to human metabolism. Nitrogen, known as element 7 on the periodic table, constitutes approximately 78% of the Earth's atmosphere, forming a vast, invisible ocean of gas that exerts a constant pressure of nearly 15 pounds per square inch upon every surface of the human body. Despite its ubiquity, this gas remains a silent and imperceptible presence, possessing no color, no odor, and no flavor. It is a material that defines the very boundaries of the world's habitable zone, yet it exists in a state of chemical isolation, refusing to participate in the rapid oxidative reactions that power biological life. This paradoxical substance is essential for the construction of every strand of DNA and every protein in the human frame. Yet in its atmospheric form, it is one that can extinguish a human life with terrifying efficiency and zero warning. The historical designation of this element as __2__, a term derived from the Greek word meaning __3__, reflects a profound understanding of its role. In the absence of oxygen, when a person enters an environment composed of pure nitrogen, the biological response is not one of panic or struggle, but of immediate and silent physiological failure. The human brain does not possess a sensory mechanism to detect the absence of oxygen. Instead, the sensation of __4__, is triggered exclusively by the accumulation of carbon dioxide in the bloodstream. In an atmosphere of pure nitrogen, carbon dioxide is still successfully exhaled from the lungs, meaning the body's alarm system never activates. A person breathing pure nitrogen will experience a rapid depletion of oxygen in the blood, a state known as hypoxia, without any accompanying feeling of air hunger. Within 2 or 3 breaths, the oxygen concentration in the brain drops below the threshold required for consciousness, leading to a sudden loss of motor function and a terminal collapse into a state of permanent neurological cessation. This lack of a biological warning system makes nitrogen one of the most effective and invisible hazards in industrial and laboratory settings, a silent atmospheric displacer that claims lives by simply being present where oxygen is expected to be. This indifference to human biology is a direct consequence of the molecular structure of nitrogen gas, which exists as a diatomic molecule, N2. The 2 nitrogen atoms are fused together by a triple covalent bond, one of the strongest and most stable chemical bonds in the natural world. This triple bond requires a massive input of energy to break, rendering atmospheric nitrogen almost entirely inert at standard temperatures and pressures. While oxygen is highly reactive and prone to causing combustion and oxidation, nitrogen acts as a stabilizing buffer, preventing the Earth's atmosphere from becoming a flammable hazard and providing the structural bulk of the planetary environment. However, this stability also creates a significant biological barrier. Most organisms, including humans, lack the chemical machinery necessary to break the nitrogen triple bond and utilize the element for nutritional purposes. Every nitrogen atom currently residing in the complex proteins of the human heart or the nitrogenous bases of the genetic code had to be fixed, transformed from its inert gaseous state into a reactive chemical compound, through processes that involve either the extreme energy of lightning strikes or the sophisticated enzymatic pathways of specialized soil bacteria. The modern human experience is defined by a successful, yet violent circumvention of this natural nitrogen limitation. The current global population of 8 billion people is only sustainable because of the industrial capacity to crack the nitrogen triple bond on a massive scale, a process that consumes approximately 1 to 2% of the world's total annual energy production. This transition from a world of nitrogen scarcity to one of nitrogen abundance represents the most significant chemical intervention in the history of the species. It has allowed for the expansion of the human population far beyond the natural carrying capacity of the Earth, effectively, "7 the atmosphere to build human bodies." Yet, the same technology that allows for the mass production of synthetic fertilizers also provides the primary ingredient for every major non-nuclear explosion in human history. The nitrogen atom, once liberated from its atmospheric prison, becomes a highly energetic and volatile component of gunpowder, TNT, and modern high explosives. This duality, the ability to both sustain a global population and provide the means for its total destruction, positions nitrogen as the most strategically significant element in the history of geopolitics. The mastery of this element is the hidden foundation of the modern technological era. From the cryogenic cooling required for quantum computing and medical imaging to the inert atmospheres that preserve the global food supply, the manipulation of element 7 is a constant, though unseen, requirement for the functioning of global society. We are a species that lives on the floor of a nitrogen-filled pressure vessel, using the very "8" that could kill us to drive our progress. The story of nitrogen is the story of how humanity learned to negotiate with an element that was never designed to be part of our biological reality. It is a material that requires absolute precision and respect, as it remains perfectly capable of returning to its silent, inert, and life-extinguishing state the moment our technological control falters. To ensure the continued exploration of these deep scientific realities and the intricate connections between chemistry and human survival, engagement with the content is essential. By subscribing to the channel and providing a comment with the phrase __quote_9__, the audience directly assists in maintaining the visibility of these educational narratives within the digital ecosystem. The support of the viewer is the primary mechanism that prevents this information from being lost in the vast, entropic noise of the algorithmic landscape, mirroring the way nitrogen itself maintains the structural integrity of our atmosphere. The physical properties of nitrogen gas are governed by the laws of thermodynamics, in a way that creates a unique atmospheric stability. With a molecular weight of 28.01 atomic mass units, nitrogen is slightly lighter than oxygen, yet its overwhelming abundance ensures a uniform distribution throughout the lower atmosphere. This distribution is vital for the regulation of the Earth's climate and the protection of its surface. Nitrogen molecules are highly effective at scattering shorter wavelengths of light, contributing to the blue coloration of the sky and helping to diffuse the intense solar radiation that would otherwise cause extreme temperature fluctuations between day and night. Furthermore, the high specific heat capacity of nitrogen allows the atmosphere to act as a massive thermal reservoir, absorbing and redistributing heat across the planet's surface. Without this vast, "10", the Earth would experience the same violent temperature swings seen on planets with thinner or non-existent atmospheres, making the development of complex life impossible. In the context of industrial engineering, the inert nature of nitrogen is utilized to create safety where there would otherwise be catastrophe. In chemical plants and fuel storage facilities, nitrogen is used for "11", and "12", a process where oxygen is replaced by nitrogen to prevent the possibility of combustion or explosion. This application relies on the nitrogen atom's refusal to bond with other elements under normal conditions, creating an atmosphere of indifference that suppresses chemical reactivity. Similarly, the aerospace industry uses nitrogen to pressurize the fuel tanks of rockets and aircraft. ensuring that as fuel is consumed, the resulting void is filled with a gas that will not react with the remaining volatile liquids. This same principle of chemical apathy is what makes nitrogen the ideal medium for the long-term preservation of everything from high-value museum artifacts to the crispness of snacks in the grocery store. By removing oxygen and replacing it with nitrogen, the process of oxidation, and therefore decay, is effectively halted. However, the transition from nitrogen as a protector to nitrogen as a hazard is a matter of concentration and pressure. In the field of deep-sea diving, nitrogen becomes a potent neurotoxin when inhaled at high partial pressures. As a diver descends, the increased atmospheric pressure forces nitrogen to dissolve into the tissues and blood in higher quantities. Beyond depths of 30 meters, this excess nitrogen begins to interfere with the transmission of electrical signals between neurons, leading to a condition known as nitrogen narcosis. The symptoms are remarkably similar to alcohol intoxication, characterized by impaired judgment, euphoria, and a loss of motor coordination. This rapture of the deep is a stark reminder that even the most inert and benign substances can become lethal when the fundamental physics of the environment are altered. If a diver ascends too quickly, the dissolved nitrogen forms bubbles in the bloodstream and joints, much like the carbonation escaping a bottle of soda, leading to the bends, or decompression sickness, a condition that can cause permanent joint damage, paralysis, or death. The extraction of nitrogen from the air is itself a feat of modern physics known as fractional distillation. To isolate the gas, ambient air must be filtered, compressed, and cooled to temperatures below -196 degrees Celsius. At this extreme thermal threshold, nitrogen undergoes a phase transition from a gas to a clear, colorless liquid. This liquid nitrogen is the lifeblood of the cryogenic industry, providing the intense cooling necessary to maintain the superconducting state of magnets in MRI machines and to preserve biological samples at a cellular level. The sheer volume of nitrogen gas produced by the evaporation of just 1 liter of liquid, approximately 700 liters, demonstrates the immense kinetic energy stored within the gas at room temperature. This rapid expansion is a property that humanity has learned to exploit for both safety, in the case of automotive airbags, and for scientific exploration, in the creation of ultra-cold environments that allow us to study the behavior of matter at the limits of physics. As we move deeper into the analysis of element 7, it becomes clear that we are not merely breathing air. We are interacting with a complex, high-energy material that defines the limits of our biological and technological existence. Nitrogen is the silent dictator of the atmosphere, a gas that manages the Earth's energy balance and provides the raw materials for our very existence, while remaining completely detached from the metabolic fires it surrounds. It is an element that demands a sophisticated understanding of both chemistry and physics, as its role in our lives is mediated by the strength of a triple bond that remained unbroken for billions of years until the dawn of the industrial age. The following blocks will explore how this, quote, 16 element was forged in the hearts of stars, and how its eventual, quote, 17 by human science led to both the greatest triumph and the darkest tragedy of the 20th century. The story of nitrogen is the story of a species learning to breathe in an ocean of, quote, 18, and finding a way to turn that emptiness into the very fuel of life. The origin of nitrogen within the cosmic chronological framework is not a result of the primary nucleosynthesis that occurred during the Big Bang, nor is it a simple byproduct of the standard fusion processes found in smaller stars like the Sun. Instead, element 7 is a product of more advanced stellar evolution, acting as a critical catalyst in the thermonuclear engines of massive stars. While the Sun primarily generates energy through the proton-proton chain, fusing hydrogen into helium through a direct sequence of collisions, stars that possess a mass greater than approximately 1.3 times that of the Sun utilize a far more complex and efficient mechanism known as the carbon-nitrogen-oxygen (CNO) cycle. In these massive stellar furnaces, Nitrogen serves as an essential intermediary. It is not consumed in the reaction, but facilitates the transformation of hydrogen into helium by acting as a nuclear substrate. This process involves a sequence of proton captures and beta decays, where carbon-12 is transformed into nitrogen-13, then carbon-13 followed by nitrogen-14, and eventually oxygen-15, before cycling back to carbon. Nitrogen-14, the most stable and abundant isotope, is the quote 19 of this cycle. Because its capture of a proton is the slowest step in the entire sequence, nitrogen accumulates in vast quantities within the cores of these stars. When these massive stars eventually reach the end of their lifespans and explode as supernovae, they eject this accumulated nitrogen into the interstellar medium, seeding the clouds of gas and dust that will eventually coalesce into new planetary systems. The ubiquity of nitrogen in the solar system is a testament to this heavy element seeding. While the Earth is the only planet with a nitrogen-dominant atmosphere that supports life, the element is found in staggering quantities throughout the outer reaches of the solar system. Titan, the largest moon of Saturn, possesses a thick, orange-hued atmosphere composed of 95% nitrogen, creating a surface pressure 1.5 times that of the Earth. On Pluto, nitrogen exists as a vast glacial landscape, where nitrogen ice flows in slow, geological ripples across the frozen surface. The presence of nitrogen in these disparate environments highlights its role as a fundamental structural component of planetary atmospheres. On the early Earth, nitrogen was likely delivered through volcanic outgassing and the impact of comets, gradually accumulating to form the primary atmospheric bulk as lighter gases like hydrogen and helium escaped into space. Because nitrogen does not easily react with the silicate rocks of the crust or dissolve in the oceans in the same way that carbon dioxide does, it remained in the gas phase, creating the stable, high-pressure environment necessary for the existence of liquid water and the eventual development of biological chemistry. The defining characteristic of nitrogen at the molecular level is the extreme stability of the dinitrogen molecule, N2N2. In this state, two nitrogen atoms are joined by a triple covalent bond consisting of one sigma bond and two pi bonds, a configuration that represents one of the strongest chemical pairings in the universe. The bond dissociation energy required to separate these two atoms is 941 kilojoules per mole, a value so high that the molecule is effectively immune to chemical intervention under standard atmospheric conditions. This __quote _20 is the reason nitrogen is often described as chemically __quote _21 or inert. From a thermodynamic perspective, the nitrogen molecule exists in a deep energy well. It is so content in its diatomic state that it requires a massive influx of external energy, such as the temperatures found in a lightning bolt or the specialized enzymatic environment of a biological cell, to break the bond and allow the atoms to participate in new chemical reactions. This molecular inertia is a double-edged sword. While it provides the atmosphere with its necessary stability, it also created a multi-billion-year quote 22 for the Earth's biosphere. Throughout the vast majority of deep time, life on Earth was caught in a paradoxical struggle. Nitrogen is an absolute requirement for the synthesis of amino acids, the building blocks of proteins, and nucleotides, the components of DNA and RNA. Without nitrogen, the primary machinery of life cannot be constructed. Yet, despite being immersed in an atmospheric ocean of nitrogen, early organisms had no way to access it. The evolution of life was strictly limited by the availability of fixed nitrogen atoms that had been torn away from their triple bonded partners and attached to hydrogen or oxygen. For eons, the only natural source of this fixed nitrogen was the energy of lightning. When a bolt of lightning strikes, it heats the surrounding air to temperatures exceeding 30,000 Kelvin. a level of thermal energy sufficient to shatter the N2-N2 triple bond. The freed nitrogen atoms then react with oxygen to form nitrogen oxides, which dissolve in rainwater and fall to the earth as nitrates, providing a meager and unpredictable supply of nutrients to the primitive soil. The biological breakthrough that finally addressed this nitrogen deficit was the evolution of nitrogen fixation, a process mastered by a select group of prokaryotes known as diazotrophs. These microscopic organisms, including certain species of bacteria and archaea, developed an extraordinary molecular machine called the nitrogenase enzyme. The architecture of nitrogenase is one of the most complex in the biological world, centered around a specialized cluster of iron and molybdenum atoms. This enzyme allows the bacteria to capture atmospheric nitrogen and, through a high energy expenditure of adenosine triphosphate, ATP, reduce it to ammonia. This process is chemically arduous and extremely sensitive. The presence of even trace amounts of oxygen can poison the nitrogenase enzyme, rendering it useless. To protect this vital process, many nitrogen-fixing bacteria evolved symbiotic relationships with plants, such as legumes, living inside specialized root nodules where the oxygen levels are carefully regulated by an oxygen-binding protein called leghemoglobin. The emergence of these nitrogen-fixing microbes transformed the Earth's ecology, allowing life to expand from the nutrient-poor oceans onto the land. It established the, quote, 25 a planetary scale recycling system, where nitrogen moves from the atmosphere into the soil, through the bodies of plants and animals, and eventually back to the atmosphere via denitrifying bacteria. However, even with the aid of biological fixation, the nitrogen cycle remained a bottleneck for the growth of any civilization. For thousands of years, the human population was capped by the amount of nitrogen that could be naturally fixed in the soil. Agriculture was a constant battle against nitrogen depletion. Once the available nitrates in a field were exhausted by crops, the land would become sterile, necessitating fallow periods or the use of manure to replenish the element. This __quote_26__ dictated the history of human migration, the rise and fall of empires, and the very structure of pre-industrial society. The depth of this limitation is visible in the geological record and the history of human population growth. Before the 20th century, the global human population never exceeded 2 billion people, a threshold determined by the finite amount of fixed nitrogen provided by nature. The Earth simply could not produce enough caloric energy to support more life, because the __quote_27__ of the nitrogen molecule was too difficult to break on a large scale. This created a world where nitrogen was more precious than gold. It was the limiting factor of existence. The inability to synthesize nitrogenous compounds also meant that military power was limited by the availability of natural nitrate deposits for the production of gunpowder and explosives. The geopolitical landscape of the 19th century was defined by the search for concentrated sources of fixed nitrogen, leading to the exploitation of remote islands and the ignition of conflicts over what was essentially fossilized biological waste. The thermodynamic stability of N2-N2 also plays a critical role in the planetary energy balance and the evolution of the Earth's core. Unlike many other gases, nitrogen does not readily participate in the greenhouse effect. Yet its presence provides the atmospheric density required to retain the heat generated by other gases like water vapor and carbon dioxide. Furthermore, recent scientific inquiries suggest that a significant portion of the Earth's nitrogen may be sequestered deep within the mantle and core. During the early stages of planetary formation, nitrogen may have been incorporated into the metallic iron of the core, acting as a light element that influences the core's melting temperature and its convective properties. This means that the __quote_28__ of our atmosphere may also be a hidden influencer of the Earth's magnetic field and internal heat flow. The distribution of nitrogen between the atmosphere and the deep interior is a balance that has remained stable for billions of years, providing the consistent pressure and thermal insulation necessary for the uninterrupted evolution of life. The transition from this state of natural nitrogen scarcity to the modern era of nitrogen abundance is the result of a singular, violent intervention in the molecular physics of the element. By understanding the cosmic origins of nitrogen in the CNO cycle and the extreme stability of its terrestrial form, we gain a perspective on the magnitude of the challenge that human science eventually overcame. We are living in an era where the nitrogen bottleneck has been forcibly widened, a change that has fundamentally altered the chemistry of our planet.
The nitrogen in the modern atmosphere is no longer just a passive observer of biology. It has been recruited into a global industrial process that fuels our bodies and our weapons. This cosmic and geological history reveals that nitrogen is not merely dead air, but a tightly wound molecular spring that holds the secret to both planetary stability and the explosive potential of human technology. The following blocks will examine how the quest for this forbidden nutrient led to a period of unprecedented scientific innovation and moral crisis, as humanity learned to do what only lightning and bacteria had done before: break the triple bond and unleash the power of element 7. The scale of the nitrogen molecule's influence on the history of life cannot be overstated. It is the invisible scaffolding of the biosphere. Every protein fold, every enzyme that catalyzes a reaction in the human body, and every sequence of the genetic code is dependent on the specific geometry and reactivity of the nitrogen atom. The nitrogen atoms in your body today are the same atoms that were once forged in the core of a massive star, ejected into the vacuum of space, and later trapped in the triple-bonded N2N2 molecules of the Earth's early atmosphere. They spent billions of years circulating in the air, waiting for the rare event of a lightning strike, or the chance encounter with a diazotrophic bacterium to become part of the living world. This cycle of deep time represents a level of continuity that connects the human experience directly to the largest and most energetic processes in the universe. We are, quite literally, the temporary vessels for nitrogen atoms that have been on a multi-billion-year journey from the depths of space to the fields of modern agriculture. The realization that our entire civilization is built upon the manipulation of this lazy element is a humbling reminder of our dependence on the fundamental laws of chemistry and physics. The 19th century witnessed a desperate geopolitical scramble for nitrogen that predated the modern era of oil and gas reliance, driven by an urgent need for the fixed nitrogen required to sustain both agriculture and the production of gunpowder. Because the atmosphere's vast reserves of nitrogen remained inaccessible behind their molecular triple bonds, the nations of the world were forced to look for rare geological deposits where natural processes had concentrated the element over millennia. This search led to the remote, arid islands off the coast of Peru and Chile, where the lack of rainfall had allowed massive accumulations of bird droppings, known as guano, to remain chemically stable. These deposits, built up over centuries by the Guanay cormorant and the Peruvian booby, contained high concentrations of nitrates and phosphorus, making them the most valuable resource on the planet at the time. The Guano Islands Act of 1856 in the United States and the subsequent Chincha Islands War between Spain and a South American alliance demonstrated that the major powers were willing to engage in naval warfare for the control of white gold. The quest for nitrogen was not merely a matter of farming, it was a matter of national security, as the same nitrates used to fertilize wheat fields were essential for the manufacture of the nitric acid required for military explosives. This reliance on natural deposits created a precarious global situation where the survival of industrial civilization was tied to a finite and rapidly depleting resource. By the turn of the 20th century, prominent scientists like Sir William Crookes warned that the world faced a catastrophic nitrogen famine,
that would lead to mass starvation as the South American deposits were exhausted.
The challenge was to find a way to perform the fixation of nitrogen, to replicate industrial scale what lightning and bacteria did in nature. This scientific and industrial hurdle was finally overcome by the German chemist Fritz Haber, whose work would become one of the most significant and controversial achievements in the history of science. Haber discovered that by combining atmospheric nitrogen and hydrogen gas under extreme pressures of 200 atmospheres and temperatures of 500 degrees Celsius, in the presence of an osmium or iron catalyst, he could synthesize ammonia, NH3NH3. This was the first time the atmospheric lock had been breached by human hands, allowing for the creation of bread from the air. The scaling of this laboratory success into a global industrial process was the work of Carl Bosch and the chemical giant BASF, resulting in the Haber-Bosch process. This feat of engineering required the development of entirely new materials, as the high-pressure hydrogen tended to permeate and weaken standard steel reactor vessels, a phenomenon known as hydrogen embrittlement. The solution involved creating multi-layered reactors with soft iron liners, a breakthrough that allowed for the mass production of synthetic fertilizers. Today, it is estimated that nearly half of the nitrogen atoms in the human body are derived from the Haber-Bosch process. This industrial intervention effectively decoupled human population growth from the natural limitations of the nitrogen cycle, allowing the global population to expand from 1.6 billion to over 8 billion in just over a century. However, the legacy of Fritz Haber is also defined by the dark application of this same technology, as the nitrogen synthesized in his factories was immediately repurposed for the manufacture of explosives during the First World War. Fritz Haber was a man of intense patriotic conviction, believing that a scientist belonged to the world in times of peace, but to his country in times of war.
When the Allied naval blockade cut off Germany's access to Chilean nitrates, the Haber-Bosch process became the sole reason the German war machine did not collapse within months. Beyond the production of conventional explosives, Haber turned his intellectual focus toward the development of chemical weapons, leading the first successful large-scale use of poison gas at the Second Battle of Ypres in 1915. He supervised the release of 6,000 cylinders of chlorine gas, which, being denser than air, flowed into the Allied trenches. Upon contact with the moisture in the lungs of the soldiers, the gas reacted to form hydrochloric acid, leading to a slow and agonizing death by asphyxiation. Haber viewed this not as a war crime, but as a more humane way to shorten the conflict, a rationalization that created a profound moral rift within his own family.
His wife, Clara Imova, who was herself a brilliant chemist and the first woman to receive a doctorate in chemistry from the University of Breslau, condemned his work as a perversion of science. Following the celebratory dinner for the success at Ypres, Clara committed suicide using her husband's service pistol, a tragic protest against the weaponization of the air. The duality of nitrogen as both the giver and taker of life reached its zenith in the subsequent decades. Haber would go on to receive the Nobel Prize in Chemistry in 1918 for the synthesis of ammonia, an award that sparked international outrage given his role in the development of chemical warfare. Paradoxically, the research conducted under Haber's direction for the protection of crops from pests led to the formulation of hydrogen cyanide-based pesticides. One of these formulations, later known as Zyklon B, would be used by the Nazi regime in the gas chambers of the Holocaust, a regime that eventually forced Haber, who was of Jewish descent, into exile. The story of Fritz Haber is the ultimate drama of the atomic age, illustrating how a single chemical breakthrough can simultaneously solve the problem of global hunger and provide the tools for unprecedented mass slaughter. Nitrogen is the silent witness to this moral complexity, an element that responds with equal efficiency to the production of life-sustaining wheat and the production of death-dealing gas. The role of nitrogen in the history of explosives is a study in the rapid release of stored potential energy.
Most modern high explosives, such as TNT, trinitrotoluene, and nitroglycerin, are nitrogen-based compounds. The power of an explosion is derived from the fact that nitrogen atoms are unhappy in these complex organic molecules. They are held in a state of high chemical tension, bonded to oxygen and carbon in unstable configurations. When an explosion is triggered, the nitrogen atoms immediately seek to return to their most stable state, the triple-bonded N2N2 molecule. This transition occurs at supersonic speeds, releasing a massive amount of energy and expanding the volume of the material by thousands of times in a fraction of a millisecond. The sheer strength of the N2N2 bond, which makes the gas so inert in the atmosphere, is the same force that drives the devastating power of a detonation. Alfred Nobel's discovery that nitroglycerin could be stabilized within diatomaceous earth to create dynamite allowed for the controlled use of this nitrogenous power, enabling the construction of the canals, tunnels, and mines that built the modern world, while also fundamentally changing the nature of warfare. In the contemporary era, the drama of nitrogen continues in the form of environmental and industrial challenges. The massive influx of synthetic nitrogen into the global ecosystem has created a state of nitrogen overload. While the Haber-Bosch process saved billions from starvation, the inefficiency of nitrogen uptake in industrial agriculture means that more than half of the applied fertilizer is washed away by rain. This runoff enters river systems and eventually reaches the coastal oceans, where it triggers massive blooms of phytoplankton and algae. As these organisms die and sink to the bottom, their decomposition consumes the available oxygen in the water, creating vast dead zones where no marine life can survive. The Gulf of Mexico and the Baltic Sea contain some of the largest dead zones in the world, areas where the biological balance has been completely overturned by the excess of element 7. This environmental crisis is a direct consequence of our attempt to fix the nitrogen cycle without fully understanding the long-term systemic impacts of such a massive intervention. Furthermore, the industrial production of nitrogen compounds remains a major driver of global greenhouse gas emissions. The high temperatures and pressures required for the Haber-Bosch process are typically generated by the combustion of natural gas, which also serves as the source of the hydrogen used in the reaction. This means that the production of our bread from the air is inextricably linked to the extraction of fossil fuels and the release of carbon dioxide. Additionally, the use of nitrogen fertilizers leads to the emission of nitrous oxide, N2O, from the soil, a potent greenhouse gas with a global warming potential nearly 300 times that of carbon dioxide. The management of nitrogen is therefore not just a matter of food security or military power, but a central challenge in the fight against anthropogenic climate change. We are now tasked with finding a green nitrogen solution, utilizing renewable energy and electrolysis to produce hydrogen and crack the nitrogen bond without the heavy environmental cost. The historical trajectory of nitrogen, from the guano wars to the laboratory of Fritz Haber and on to the modern industrial farm, reveals a pattern of human intervention that is both brilliant and perilous. We have taken an element that was designed by the universe to be a stable, inert background to life and transformed it into the most volatile variable in our survival. The madness of the 19th century nitrate scramble has been replaced by a quiet global reliance on a chemical process that most people have never heard of, yet which supports the existence of every second person on the planet. Nitrogen does not care for our moral dilemmas or our environmental concerns. It simply obeys the laws of thermodynamics. It will remain in its unstable reactive state only as long as we continue to pump energy into the system, and it will return to its triple-bonded silence the moment that energy is withdrawn. This makes element 7 a constant reminder of the fragility of our industrial civilization, a civilization that is, quite literally, built out of thin air. The following blocks will delve into the hidden ways nitrogen functions in our daily lives, from the safety systems in our cars to the cold storage of our digital data, showing that the atomic age of nitrogen is far more pervasive than we realize. The transition from the historical and geopolitical drama of nitrogen to its role in the contemporary technological landscape reveals a substance that functions as a silent, structural stabilizer for modern life. While the massive industrial synthesis of ammonia supports global food security, the unique physical and chemical properties of element 7 are utilized in a variety of specialized applications that remain largely invisible to the average person. These applications rely on the element's fundamental inertness, its refusal to participate in the rapid, often destructive oxidative reactions that characterize an oxygen-rich environment. This, quote 48, allows nitrogen to act as a protective barrier, a cryogenic coolant, and a precision-timed mechanical propellant. In every instance, the utility of nitrogen is derived from its molecular stability, a property that is exploited to manage extreme temperatures, prevent the degradation of materials, and save human lives in the fractions of a second that define an emergency. One of the most critical, yet least acknowledged, applications of nitrogen is found in the automotive safety systems that protect millions of drivers every day. When a vehicle undergoes a sudden deceleration indicative of a collision, the airbag system must deploy with a velocity and force that can cushion a human head before it impacts the steering wheel or dashboard.
This process occurs within approximately 30 to 50 milliseconds, faster than the blink of a human eye. To achieve this speed, the system does not rely on a canister of compressed air, which would be too slow and bulky. Instead, it utilizes a rapid chemical reaction involving sodium azide, NaN3NaN3. Upon receiving an electrical signal from the crash sensors, a small heating element triggers the decomposition of the solid sodium azide, which instantly breaks down into metallic sodium and a massive volume of pure nitrogen gas. This is a controlled chemical explosion where nitrogen is the primary product. The gas expands with such intensity that it inflates the nylon bag at speeds exceeding 300 kilometers per hour. The choice of nitrogen for this task is dictated by its stability. Unlike oxygen, it will not contribute to a fire following the crash, and unlike carbon dioxide, it is non-toxic when released into the vehicle's cabin. This life-saving mechanism is a direct application of the rapid expansion properties of a gas that was once trapped in a solid molecular matrix. The thermal properties of nitrogen, particularly in its liquid state, serve as the foundation for the field of cryogenics, which is essential for the functioning of modern medical and scientific infrastructure. When nitrogen is cooled to temperatures below -196 degrees Celsius, it becomes a clear, colorless liquid with an extraordinary capacity to absorb heat. In a modern hospital, liquid nitrogen is the blood that allows magnetic resonance imaging, MRI, scanners to function. These machines rely on superconducting magnets to generate the powerful magnetic fields required to visualize the internal structures of the human body. Superconductivity is a state where certain materials lose all electrical resistance, but this state can only be maintained at temperatures close to absolute zero. Liquid nitrogen is used as a primary coolant to shield the even colder liquid helium that surrounds the magnets, preventing the helium from boiling off and ensuring the stability of the magnetic field. Without the continuous presence of this cryogenic nitrogen, the superconducting state would collapse, a process known as a quench, potentially damaging the multi-million-dollar equipment and rendering diagnostic imaging impossible. The same cryogenic capacity is utilized in the long-term preservation of biological materials, a process known as vitrification. By rapidly cooling cells or tissues with liquid nitrogen, the water within the cells is transitioned into a glassy state without the formation of ice crystals. Ice crystals are lethal to biological structures because they expand and puncture cell membranes. By bypassing this crystalline phase, nitrogen allows for the indefinite storage of reproductive cells, stem cells,
and rare genetic samples. This biological pause is the mechanism behind modern fertility treatments and the global efforts to preserve the biodiversity of the planet through seed and gene banks. In this context, nitrogen acts as a temporal anchor, holding biological life in a state of suspended animation for decades or even centuries, perfectly preserved against the entropic decay of time. In the realm of digital infrastructure, nitrogen serves as a critical component in the protection and maintenance of the massive data centers that facilitate the global internet. The density of electronic components in a modern server farm generates immense quantities of heat, making fire suppression a primary concern for engineers. Traditional water-based sprinkler systems are catastrophic for electronic hardware, leading to short circuits and the permanent loss of data. Instead, many high-security data centers utilize inergen, or pure nitrogen systems, for fire suppression. When a fire is detected, the room is flooded with nitrogen gas, which rapidly reduces the oxygen concentration from 21% to below 15%. This level of oxygen is insufficient to support combustion, effectively suffocating the fire. Yet it remains high enough to allow any personnel in the room to breathe safely as they evacuate. This application treats the atmosphere not as a source of life, but as a variable that can be manipulated to protect the physical repositories of human knowledge. The food industry utilizes the inertness of nitrogen to achieve a state of canned freshness that would be impossible in a normal atmosphere. This technology, known as modified atmosphere packaging, MAP, is the reason why a bag of potato chips remains crisp for months, and why pre-packaged salads do not wilt immediately upon reaching the grocery store. When a product is sealed, the ambient air, containing oxygen and moisture, is flushed out and replaced with high-purity nitrogen. Oxygen is the primary enemy of food preservation. It facilitates the oxidation of fats, leading to rancidity, and provides the necessary environment for the growth of aerobic bacteria and molds. Nitrogen, by contrast, is chemically indifferent to the organic compounds in the food. It creates a pressurized cushion that prevents the physical crushing of delicate items, while simultaneously halting the chemical processes of decay. We are, quite literally, consuming food that has been preserved in the microscopic, nitrogen-filled sanctuary, isolated from the corrosive effects of the Earth's natural atmosphere. The mechanical advantages of nitrogen extend into the high-performance worlds of aviation and professional racing. The tires of commercial aircraft and Formula One cars are never filled with compressed air, but with 99% pure nitrogen. This choice is driven by the fact that nitrogen is a __56__ gas. Compressed air contains varying levels of water vapor, which can freeze at high altitudes or expand rapidly when subjected to the intense heat of braking during a landing. Such fluctuations in pressure can lead to tire failure or the loss of structural integrity. Nitrogen, being nearly devoid of moisture and exhibiting a very low coefficient of thermal expansion, maintains a consistent pressure across a vast range of temperatures and altitudes. Furthermore, nitrogen molecules are slightly larger than oxygen molecules, meaning they migrate through the rubber structure of the tire at a much slower rate, ensuring that the tires remain properly inflated for longer periods. This technical detail, though hidden within the wheels of a Boeing 747, is a critical factor in the safety and efficiency of global transportation. The element also plays a foundational role in the manufacturing of high-tech semiconductors and microelectronics. The process of __57__ silicon wafers and creating the microscopic circuits that power every smartphone and computer requires an environment of absolute purity. Even a single atom of oxygen or a molecule of water vapor can contaminate a wafer, leading to a __58__ chip. Consequently, the entire fabrication process, known as a _59, takes place within an ultra-pure nitrogen atmosphere. Nitrogen is used to _60, the chemical vapors used in the deposition of circuit layers, ensuring that no unwanted oxidation occurs at the molecular level. The precision of modern computing is, therefore, a direct result of our ability to exclude the reactive elements of the air and replace them with the stable, predictable presence of element 7. In the industrial sector, nitrogen is utilized for its ability to manage the volatile nature of hydrocarbons. In oil tankers and refineries, nitrogen is pumped into the _61_61_ space, the empty area above the liquid fuel in a tank. By maintaining a nitrogen blanket, engineers ensure that the concentration of flammable vapors remains below the explosive limit, even if a spark were to occur. This process, known as inerting, is the primary safety protocol that prevents massive industrial disasters and ensures the safe transport of the energy resources that fuel the global economy.
Nitrogen acts as a chemical __62_, a substance that takes up space without participating in the dangerous energetic exchanges occurring beneath it. The cumulative effect of these various applications is a world that is deeply dependent on the continuous supply of a gas that most people ignore. Nitrogen is the hidden engineer of the modern era, managing the transition between extreme heat and extreme cold, between explosive force and delicate preservation. It is a material that allows us to push the boundaries of what is possible in medicine, computing, and transport, providing a layer of safety and stability that the natural environment cannot offer. We have taken the __63_ of the atmosphere and turned it into a sophisticated tool for the enhancement and protection of human life. This technological mastery is a testament to our understanding of the fundamental molecular architecture of the universe, where the strength of a triple bond is the key to creating an atmosphere of absolute control. The final block will examine the broader environmental consequences of this control as we follow the cycle of nitrogen back into the ecosystem and consider the long-term impact of our intervention in the planetary balance. We will explore how an element that brings stability to our machines can bring chaos to our oceans, revealing the ultimate cost of our dependency on element 7. The transition from industrial utility to ecological disruption represents the final and perhaps most significant chapter in the human relationship with nitrogen. While the Haber-Bosch process effectively eliminated the natural __64_ that had constrained human populations for millennia, it simultaneously introduced a massive, unregulated flux of reactive nitrogen into the global environment. This phenomenon has resulted in the doubling of the natural rate of nitrogen fixation on Earth, an intervention of such magnitude that it has fundamentally altered the chemical equilibrium of the planet. In the natural order, the nitrogen cycle is a closed and balanced system, where the amount of nitrogen fixed by lightning and bacteria is precisely offset by the process of denitrification, where specialized microorganisms convert nitrates back into the stable, triple-bonded N2N2 gas. However, the modern industrial output of synthetic fertilizers and the combustion of fossil fuels, which creates nitrogen oxides as a byproduct, have overwhelmed this natural recycling mechanism. The excess reactive nitrogen does not simply vanish. It migrates through the soil, the atmosphere, and the water, creating a cascade of environmental effects known as the __65_, where a single atom of reactive nitrogen can contribute to a sequence of negative impacts ranging from smog and acid rain to the catastrophic depletion of oceanic oxygen. The most visible manifestation of this imbalance occurs in the world's aquatic ecosystems,
through a process known as eutrophication.
When synthetic nitrogen fertilizers are applied to industrial croplands, the uptake by plants is often highly inefficient, with significant portions of the nitrates leaching into the groundwater or being carried by surface runoff into river systems. As these nutrient-rich waters reach the coastal oceans, they act as a potent stimulant for the rapid growth of phytoplankton and macroalgae. This sudden biological explosion, often referred to as an __66__, creates a dense green or red carpet across the surface of the water, blocking sunlight and disrupting the local food web. The true catastrophe begins when these algae reach the end of their brief lifespans and sink to the ocean floor. At this depth, aerobic bacteria begin the process of decomposition, a chemical reaction that consumes immense quantities of dissolved oxygen. In areas with high nitrogen input and low water circulation, the oxygen concentration can drop to levels below 2 milligrams per liter, a state known as hypoxia. These __67__
are currently found in over 500 locations globally, covering hundreds of thousands of square kilometers in regions such as the Gulf of Mexico, the Baltic Sea, and the East China Sea. In these zones, the __68__ of the atmosphere has created a biological vacuum where fish, crustaceans, and other marine organisms must either flee or perish from asphyxiation. Beyond the aquatic environment, the oversaturation of the planet with reactive nitrogen is a significant, yet often overlooked, driver of anthropogenic climate change. While the primary focus of climate science is frequently directed toward carbon dioxide, the role of nitrous oxide, N2O, is becoming increasingly critical. Nitrous oxide is a byproduct of the microbial breakdown of nitrogen fertilizers in the soil, and its impact on the global energy balance is profound. Molecule for molecule, nitrous oxide is approximately 300 times more effective at trapping infrared radiation in the atmosphere than carbon dioxide over a 100-year timescale. Furthermore, nitrous oxide has a long atmospheric residency time, remaining stable for over a century before it is eventually broken down in the stratosphere. During its degradation, it releases nitrogen oxides that actively participate in the destruction of the ozone layer, which shields the Earth's surface from lethal ultraviolet radiation. The nitrogen that was once fixed to provide food for the human population is now, through the complex chemistry of the atmosphere, contributing to the gradual destabilization of the very climate that made agriculture possible. The scale of this chemical intervention has led many scientists to identify the nitrogen cycle as one of the primary planetary boundaries that has already been exceeded. The concept of planetary boundaries defines the safe operating space for humanity, based on the stability of the Earth's natural systems. Research indicates that the current rate of anthropogenic nitrogen fixation is more than double the level considered sustainable for the long-term health of the biosphere. We are currently operating in a state of high uncertainty, where the cumulative effects of nitrogen overload may lead to irreversible tipping points in biodiversity and soil health. The acidification of soils, the loss of plant species diversity in nitrogen-saturated forests, and the alteration of the global microbial community are all indicators that the element which enabled the rise of modern civilization is now testing the limits of the planet's resilience. The nitrogen atom, in its reactive form, is an uncompromising agent of change, indifferent to the structural requirements of the ecosystems it inhabits. This environmental reality forces an existential re-evaluation of the success of the Haber-Bosch process. We have achieved a state of unprecedented demographic expansion by bypassing a fundamental limit of nature, but we have done so by creating a massive chemical debt that must eventually be reconciled. The nitrogen paradox lies in the fact that we cannot survive without the industrial fixation of this element, yet we are struggling to manage the consequences of its abundance. This situation necessitates the development of a new, circular nitrogen economy, where the efficiency of fertilizer use is maximized, and the recovery of nitrogen from waste streams becomes a standard industrial practice. The goal is to move from a linear mine and dump model to one that mimics the natural nitrogen cycle, returning the atoms to their stable N2N2 state before they can cause further environmental damage. This shift represents the next major challenge in the human relationship with element 7, a challenge that requires the same level of scientific brilliance that Fritz Haber once applied to the problem of nitrogen scarcity. As we look toward the distant future, the ultimate fate of nitrogen remains dictated by its thermodynamic preference for the diatomic state. If the human species were to disappear tomorrow, the massive industrial output of reactive nitrogen would cease almost immediately. The excess nitrates in the soil and water would be slowly processed by denitrifying bacteria, which utilize these compounds as electron acceptors in their metabolic pathways. One by one, the nitrogen atoms would find their way back into the atmosphere, reforming the triple covalent bonds that were so violently severed in high-pressure reactors. The dead zones in the oceans would eventually re-oxygenate as the nutrient levels normalized, and the concentration of nitrous oxide in the stratosphere would slowly decay. Within a few thousand years, a mere blink in geological time, the nitrogen cycle would return to its primordial equilibrium. The 78% concentration of nitrogen in the atmosphere would remain a constant, silent presence, unaffected by the brief period of human industrial activity. The perspective of deep time reveals that the atomic age of nitrogen is a temporary anomaly in the long history of the Earth. For billions of years, the element existed in a state of nearly perfect gaseous isolation, punctuated only by the occasional energy of a lightning bolt. The human intervention, while massive in the context of our own history, is a localized event in the thermodynamic life cycle of the planet. Nitrogen is an element that excels at waiting. Its molecular stability is so great that it can endure for eons without change, providing a consistent atmospheric pressure that shields the world while remaining largely detached from its biological processes. We are the ones who chose to engage with this lazy gas, to break its triple lock and harness its explosive and nutritional potential. In doing so, we have made ourselves responsible for the management of a force that is far more durable and uncompromising than our own civilization. The final conclusion of the nitrogen story is one of profound objective reality. We are a species composed of stardust that has learned to utilize the dead air of the atmosphere to sustain its growth. Every cell in the human body is a temporary vessel for nitrogen atoms that have traveled from the hearts of massive stars through the vacuum of space and into the industrial infrastructure of the modern world. These atoms are currently working within the complex machinery of our DNA and proteins, but they are not our property. They are on loan from the atmosphere, held in a state of high-energy reactivity that the laws of physics are constantly trying to dismantle. When our biological processes cease, and when our industrial machines eventually fall silent, these atoms will return to the vast atmospheric ocean from which they were taken. The nitrogen will remain, invisible and tasteless, encircling the planet with its silent weight. It will continue to scatter the sunlight into a blue sky and to buffer the chemical fires of the surface, just as it did before the first life form emerged, and as it will do long after the last one vanishes. We were a momentary chemical accident that figured out how to make the dead air work for us. A species that for a brief instant learned to bake bread from the air. But nitrogen is the silent dictator that outlasts all empires. Its peace is the peace of the triple bond, a state of absolute molecular stability that requires no energy
and fears no decay. We thought we had domesticated the silent killer, but in reality, we have only borrowed a small fraction of its power. The nitrogen cycle will continue. The forbidden nutrient will return to its gaseous sanctuary, and the Earth will once again be shrouded in the indifferent, life-supporting, and life-extinguishing embrace of element 7. This is the ultimate fate of our world, a return to the leaden, nitrogenous silence from which we emerged, where the only thing that remains is the triple bond, closed once more on its eternal lock.